Welcome to The Explainer. Today we're diving into a seriously mind-bending reality about our universe. We usually think of time as this steady, unyielding metronome, just ticking away at the exact same rhythm for everyone, everywhere. But what if I told you that time doesn't actually tick at the same rate for everyone? What if time is actually flexible, stretching and squeezing depending on how fast you're moving, or even how far you are from a massive planet? Just think about it for a second. Does the wristwatch you're wearing right now tick at the exact same speed as a clock mounted inside an astronaut's capsule orbiting the Earth? Or what about a clock sitting way up on the peak of a mountain versus one down at sea level? Well, the answer is a resounding no. Okay, let's dive into this.
Here's our roadmap for today. First, the concept of time dilation. Second, muons as subatomic time travelers. Third, flying clocks around the world. Fourth, gravity probe A in space. And finally, the everyday impact of relativity. All right, section 1, the concept of time dilation. Abstract math meets physical reality.
For the longest time, Albert Einstein's theories of relativity were viewed by a lot of people as, well, brilliant, but highly abstract mathematical concepts. But that math translates into an undeniable physical reality through a core concept called time dilation. Basically, time dilation is the expansion or contraction in the rate at which time passes due to speed or gravity. According to relativity, matter literally distorts the space-time around it. But there are two distinct flavors of this phenomenon that we really need to understand. On one side, we have kinematic time dilation, which comes from special relativity. This tells us that if a clock is moving at a really high speed relative to an observer, that moving clock runs slower. Simply put, speed slows time down. On the flip side, we have gravitational time dilation, which stems from general relativity. This dictates that a clock sitting higher up in a gravity well, say high up in the atmosphere where Earth's gravity is slightly weaker, will actually run faster than a clock deep down on the Earth's surface. Now, you might be wondering, if this is all true, why don't I ever notice my watch slowing down when I'm blasting down the highway? Well, it's because everyday speeds and gravity changes are just entirely too small. To put that into perspective, a watch on a walking man loses only about 1 second every billion years compared to someone standing still. Even an astronaut in an orbital capsule traveling at 7 kilometers per second loses only 1 single second in a typical human lifetime. So to actually measure this stuff, we need extreme speeds, extreme altitudes, and incredibly precise clocks. Moving on to section 2, muons, subatomic time travelers, proving relativity on Mount Washington. Back in 1963, physicists David Frisch and James Smith needed a way to measure time at speeds approaching the speed of light. So they used subatomic particles called muons, which get created high up in the atmosphere by cosmic rays. It's kind of like the radioactive decay of these particles acts as a tiny, built-in alarm clock. A specific number of them decay over a set average time. The scientists realized that if they could count the muons at a high altitude and then count the survivors down at sea level, they could use the rate of radioactive decay to see if the clocks of the moving muons were running slower than clocks at rest. To pull this off, they went all the way up to the top of Mount Washington in New Hampshire and counted the muons raining down at 0.995 times the speed of light. Then, they hauled their scintillator equipment down to sea level in Cambridge, Massachusetts, and counted again. They physically recorded the decay pulses of these particles on oscilloscope traces, and the results? The fast-moving muons decayed way more slowly than they would have if they were just sitting at rest. Actually, their time was dilated by a factor of 8.8. Time was literally passing slower for these subatomic particles just because they were moving so incredibly fast. Okay, section 3, flying clocks around the world. The Hafele Keating experiment. So, scientists naturally wanted to test this on a human scale using physical mechanical clocks. Physicist Joseph Hafele and astronomer Richard Keating managed to scrape together a super meager $8,000 budget from the Office of Naval Research for what would become one of the most cost-effective tests of general relativity ever done. Get this, they spent a whopping $7,600 of that budget just on commercial airline tickets. They literally bought window seats for 4 cesium beam atomic clocks, which they hilariously booked under the name Mr. Clock. They flew these highly sensitive atomic clocks entirely around the world twice, once eastward and then once westward, and then compared them to stationary clocks left back at the US Naval Observatory. And this brilliantly illustrates exactly what happens when relativity meets commercial air travel.
When flying eastward in the same direction as the Earth's rotation, the clocks had a faster total speed relative to the Earth's center. That means kinematic time dilation made them lose time. They measured a loss of about 59 nanoseconds. But flying westward against the Earth's rotation, their net speed was slower, so the gravitational time dilation from being at a high cruising altitude took over. They gained 273 nanoseconds. These measured numbers matched the relativistic predictions to within roughly 10% precision. The physics world had absolute consensus. Relativity was visibly, mathematically verified by clocks flying in coach on passenger jets.
Next up, Section 4, Gravity Probe A in space. Escaping Earth's gravity well. To test the effects of gravity on time with even greater precision, NASA and the Smithsonian Astrophysical Observatory realized they needed to go way higher than a commercial airliner. They needed to fully escape the Earth's gravity well. So, on June 18, 1976, they launched Gravity Probe A on a Scout rocket out of Virginia. They shot this spacecraft nearly vertically to an altitude of 10,000 kilometers. That's about 6,200 miles, straight up. The whole mission only lasted 1 hour and 55 minutes before it splashed down in the Atlantic Ocean. But tucked inside that probe was an atomic hydrogen maser, which is an incredibly accurate clock that generates a microwave signal. Now, just how accurate was this hydrogen maser? It had a stability of 1 part in a quadrillion. That is 10 to the power of 15. To put that completely staggering number into a relatable scale, a clock this stable would drift by less than 2 seconds over the course of 100 million years. Mind-blowing, right? During the flight, a continuous microwave signal was sent between the space probe and an identical maser clock on the ground. By meticulously canceling out the Doppler shift caused by the rocket's motion, scientists were left with pure gravitational time dilation. And, exactly as predicted, high up in the weaker gravitational potential at 10,000 kilometers, the clock in space ran 4.5 parts in 10 to the 10th faster than the clock on Earth. This confirmed Einstein's theory of general relativity to an accuracy of 70 parts per million. Time truly does flow faster the further away you get from a massive object like our planet. Finally, Section 5, the everyday impact of relativity. Why this matters to you today. So we've talked about subatomic particles, atomic clocks on airplanes, and rockets in space. But why does any of this matter to you today? The crucial takeaway here is that relativity isn't just some quirky scientific parlor trick. It literally powers modern infrastructure. Take the Global Positioning System, or GPS. The satellites powering the navigation on your phone are orbiting Earth at extremely high speeds, and they're high up on a weaker gravitational field. If engineers didn't actively incorporate the exact mathematical formulas for both velocity time dilation and gravitational time dilation into the GPS software, the clocks on the satellites and the clocks on Earth would desynchronize immediately. Without Einstein's math, your smartphone's maps would be utterly useless within a matter of minutes, drifting by miles every single day. It's absolutely remarkable to look back at Albert Einstein's original 1905 paper on special relativity. He proposed a theoretical thought experiment about spring clocks at the equator versus the poles. He didn't have the technology to actually prove it at the time, but he knew the math demanded it. Decades later, whether it was muons decaying on a mountain, Mr. Clock flying coach, or a hydrogen maser shot out of the atmosphere on a rocket, that abstract thought experiment became heavily verified, irrefutable physical reality. As we wrap up this explainer, I want to leave you with something to chew on. We move through our days just assuming our time is identical to everyone else's, but the universe is wonderfully weird. The next time you're flying on a commercial airplane or even just driving down the highway, look down at your watch. Because at that very moment, however slightly, your personal flow of time is bending, stretching, and reacting to the fabric of space-time itself. Thanks for joining me on this journey, and keep questioning the reality around you.